Have you ever gazed up at the night sky, filled with countless stars, and wondered what it would be like to visit them? Our universe is vast, almost incomprehensibly so. The nearest star to our own, Proxima Centauri, is over 4 light-years away. This means that even if we could travel at the speed of light, it would still take us more than 4 years to get there. To reach the Andromeda Galaxy would take a staggering 2.5 million years. These immense distances make interstellar and intergalactic travel seem like an impossible dream, a fantasy confined to the pages of books and the silver screen. But what if there was a shortcut? Imagine a secret passage through the fabric of the universe, a cosmic tunnel that could connect 2 distant points in space and time. This is the tantalizing promise of a wormhole. Instead of traveling the long way around, a wormhole could offer a direct path. You could step into one end here in our galaxy and emerge moments later on the other side of the universe, turning journeys that would take millions of years into something accomplished in the blink of an eye. This concept isn't just a flight of fancy. It has roots in some of the most profound scientific theories ever conceived. The idea of these cosmic shortcuts, officially known as Einstein-Rosen bridges, emerged from the mind of Albert Einstein himself. For many of us, our first encounter with the idea of a wormhole was not in a physics textbook, but through popular culture. Films and television shows like Stargate, Interstellar, and Star Trek have made wormholes a staple of science fiction. They're often portrayed as shimmering portals or stable gateways, providing a convenient plot device for heroes to journey to distant galaxies in a matter of moments. These fictional depictions, while thrilling, often simplify the immense complexities involved. The reality, according to our current understanding of physics, is far more challenging and uncertain. The journey to understand wormholes begins not with starships, but with gravity. It was Albert Einstein's theory of general relativity that first opened the door to this possibility. His theory revolutionized our understanding of gravity, showing that it isn't a force pulling objects together, but rather a curvature in the fabric of space-time itself. It was in exploring the mathematical landscape of his own theory that Einstein, alongside Nathan-Rosen, stumbled upon the solution that described 2 distant points in space-time connected by a bridge. To truly get to grips with the mind-bending concept of a wormhole, we first need to take a step back and reconsider everything we think we know about space. Albert Einstein, in his profound theory of general relativity, revealed a much more dynamic and fascinating picture. Think of it like a giant invisible trampoline sheet stretched out across the cosmos. This sheet represents the 3 dimensions of space and the 1 dimension of time, all interconnected. Massive objects like stars and planets warp this fabric, and other objects simply follow these curves. It's a beautifully intricate relationship that governs the entire universe. Before Einstein, our understanding of gravity was dominated by the brilliant work of Sir Isaac Newton. However, despite its success, Newton's theory had some puzzles it couldn't solve. One of the most famous was the peculiar orbit of Mercury. When Einstein applied his equations to Mercury's orbit, they predicted the exact amount of precession that had been observed for decades. It was a stunning confirmation of his theory. This concept that space-time itself can be bent and shaped is the key that unlocks the theoretical possibility of cosmic shortcuts. If you can bend space-time, perhaps you can fold it, connecting 2 distant points directly. The science behind wormholes is, at its core, a story told in the language of mathematics. It all stems from Albert Einstein's field equations for general relativity, a set of 10 interrelated differential equations that describe the fundamental interaction of gravitation. In 1935, Einstein and his colleague Nathan-Rosen were exploring these solutions. They realized that the mathematics didn't just describe a single funnel-like depression in space-time. Instead, it described 2 such funnels, connected at their narrowest points, the singularities. However, the initial Einstein-Rosen bridge was found to be unstable and non-traversable. It would collapse before anything could pass through it. The throat of the wormhole would open and then pinch off so quickly that not even a single photon of light would have time to travel from one end to the other. To create a stable, open tunnel, you would need to find a way to prop the throat open and counteract the immense gravitational forces trying to crush it. This would require something truly extraordinary, a form of matter with properties unlike anything we have ever observed in our universe. The sheer quantity of this hypothetical material required is staggering. To create a wormhole with a throat just 1 meter across, you would need an amount of negative energy equivalent to the total energy output of a star over a very long period. While the strange world of quantum mechanics offers a glimmer of hope through effects like the Casimir effect, it is a colossal leap from these microscopic effects to gathering enough stable exotic matter to hold a human-sized wormhole open. The conversation about wormholes often focuses on their potential for interstellar travel, for bridging vast distances in space. However, their implications might be even more profound, extending beyond space to the dimension of time itself. By manipulating one end of the wormhole through relativistic effects, you have successfully transformed a spatial bridge into a temporal one. The wormhole has become a gateway to yesterday and tomorrow. The possibility of using a wormhole to travel into the past immediately opens a Pandora's box of logical contradictions known as temporal paradoxes. The most famous of these is the grandfather paradox. The unsettling nature of time travel paradoxes has led some of the world's most brilliant physicists to propose that there might be a fundamental law of nature that prevents them from occurring. The late great Stephen Hawking was a prominent proponent of this idea, which he called the chronology protection conjecture. Theoretical calculations by physicists have shown that the moment a wormhole is manipulated in a way that would allow for time travel, quantum vacuum fluctuations would rush into the wormhole, generating a catastrophic burst of energy that would obliterate the wormhole just before it becomes a time machine. History would be safe, not because of a mysterious force, but because of the fundamental physics of space-time itself. The universe wouldn't need a conscious will to prevent time travel. The very laws of quantum field theory and general relativity, when combined, would automatically shut down any such attempt. Science fiction has long been fascinated by the concept of the wormhole, using it as a convenient and visually spectacular device to overcome the vast distances of space. In films like Interstellar or the television series Stargate SG-1, wormholes are often depicted as shimmering, stable portals or turbulent but navigable tunnels of light. This portrayal serves a vital narrative purpose, enabling epic stories that span the cosmos without getting bogged down in the tedious reality of multi-generational space travel. The roller coaster ride is a cinematic invention to make the instantaneous seem epic. While films like Interstellar make a commendable effort to ground their wormhole in real theory, advised by physicists like Kip Thorne, they still ultimately prioritize the dramatic needs of the story. The Hollywood wormhole is a tool for storytelling, a symbol of humanity's ability to conquer the final frontier, rather than a rigorous exploration of a complex scientific hypothesis. Despite the many liberties taken, there are fascinating areas where science fiction and real scientific theory overlap. Carl Sagan's novel, Contact, and the subsequent film, is a perfect example. Sagan's desire for a scientifically plausible method of interstellar travel for his story led him to consult with physicist Kip Thorne. Ultimately, science fiction and scientific theory share a symbiotic relationship. Science provides the fascinating concepts and possibilities that fuel the imagination of writers and filmmakers. In return, science fiction popularizes these ideas, inspiring new generations to become scientists and pushing the boundaries of what we dare to imagine. While Hollywood's wormholes may be fantastical, they share a common origin with the real theories, a profound sense of wonder about the cosmos and our place within it. So, after our long journey from science fiction to the frontiers of theoretical physics, where do we stand on the question of wormholes? The honest answer, at this moment in our scientific understanding, is that we simply do not know for sure. The concept of a wormhole rests on the solid foundation of Albert Einstein's general relativity, our most successful theory of gravity. The mathematics allows for their existence, painting a tantalizing picture of a universe stitched together by hidden cosmic tunnels. However, the path from a mathematical solution to a physical object is a long and uncertain one. The dream of a stable, traversable wormhole requires exotic matter with negative energy density, a form of matter that possesses a kind of anti-gravity. The problem is that no such substance has ever been observed. Looking to the future, the quest to understand wormholes will continue to drive scientific innovation and discovery. The implications of discovering a real wormhole would be nothing short of revolutionary. It would be the single greatest discovery in human history, changing our place in the universe forever. The ability to travel between stars would transform us from a planetary species into a truly galactic one, opening up countless new worlds for exploration and perhaps one day for habitation. It would solve the problem of cosmic distances, the greatest barrier to our expansion into the universe. But beyond the practicalities of travel, the study of wormholes forces us to contemplate our own existence in a deeper way. It makes us grapple with the nature of space, the flow of time, and the very fabric of causality. In the end, whether we ever build a starship to traverse an Einstein-Rosen bridge or not, the idea itself serves a vital purpose. It is a testament to human curiosity, our innate desire to explore, to understand, and to reach for the impossible. From science fiction dreams to the complex equations of theoretical physics, the wormhole represents our unending quest to look up at the night sky and see not a barrier, but an invitation. The journey to understand these cosmic shortcuts is a journey to understand the universe itself, and it is a journey that has only just begun. The truth is still out there, waiting among the stars.